Section 8.3, Trigonometric Integrals. Obviously, your trig is going to be important in this section. Lots of formulas and identities you need to remember. One of the most important ones will be a double angle formula for cosine, which if you remember the basic cosine squared of A minus sine squared of A, you can do a Pythagorean theorem substitution for cosine squared and get this formula, which allows you to solve for sine squared easily. Or we can take this one and do a substitution for sine squared, which lets us have cosine squared, and that's going to matter in our integrals coming up. So our integration gets more involved, and your commitment to memorization of trigonometric identities and your unit circle values and trigonometric integration rules up to this point will determine the ease with which you adjust to this material. If you have not really gotten this material solidly in your brains, it is not too late, but you must get it down now. I will not be giving you any formulas on this or any future exams, so you need to know it. So again, identities you should know. Of course, your Pythagorean identities and be able to change them algebraically. Product to sum, you might use these not as often as double angle. And then power reduction. And I just showed you the way that we can get these coming from this up here. I can solve for sine squared by dividing by 2. I can solve for cosine squared by dividing by 2, and that gives you your power reduction identities that we'll be using. So let's see how we can do one of these. If we notice, I look at sine here and cosine in my integrand. We know that cosine is the derivative of sine. I might think of doing sine of 7x is my u, and then my du would be 7 cosine 7x. I don't have the 7x here, so I cannot do this with my u being sine of 7x. But I can look at product to sum. This is a product, and I'm going to change it to a sum so I can integrate. So I'm going to let my alpha be 7x, my beta be 3x, and using our identity from above that sine alpha times cosine beta is 1/2 sine of alpha minus beta plus sine of alpha plus beta. And now I'm going to let my u be 4x and my v be 10x and write two separate integrals and get them in the right form so that I can anti-differentiate nicely. You might need to ponder this a while. So let's look at this one. The integral of sine x to the 4th times cosine x to the 5th dx. All right, I am going to split off a factor of cosine. This gives me an even power on this cosine, which I can write as cosine squared squared. And why would I do that? Because I can make a Pythagorean substitution for cosine squared. And now I can square this binomial and distribute sine across it. Now let's look at what I have. I have a bunch of terms with sine in it and cosine x dx. Now we know that if our u is sine, the derivative is cosine x dx. So I have basically created my derivative for each of these terms right here. So I'm going to think about 3 separate integrals. And I can integrate each of these. This is u to the 4th du, u to the 6th du, u to the 8th du. Very nice. So we can develop some basic rules that will help us in situations like this. When you have a product of sine and cosine, if the exponent on cosine is odd, split off a factor of cosine, put the Pythagorean identity in, okay, and do your substitution where your u is going to be sine x, therefore your du would be your cosine x dx. If m is odd, do the same thing, but splitting off a factor of sine, use this substitution, and your u would be cosine of x, and then your derivative would be negative sine x dx. If m is even and n is even, then we're going to use these power reduction formulas. And again, these have their foundation in the double angle formula for cosine that I discussed at the beginning of this video. So let us look at the last example, again, in light of the above rules, and use a u substitution. Now we know we got here, okay, and we know that we did our Pythagorean substitution, and we're going to let u equal sine x and du equals cosine x dx. This is just a lot cleaner looking, okay. We've anti-differentiated with u, and now I have to go back in and substitute in my x's. All right, sine cubed x times cosine fourth x dx. All right, I have an odd exponent on sine, so I'm going to split off a factor of sine, use my Pythagorean substitution there. We know that if our u is cosine, our du is negative sine of x dx, so I'm going to multiply and divide by -1. And I'm going to go ahead and do my substitution with that multiplication, knowing that I multiplied this by -1 so I could get du in there. But that required a -1 out here. And then we're going to do the necessary algebra of distributing u to the fourth and the anti-differentiation, and then go back and substitute in our function that u was standing for. All right, this is the same example as the example number 1 in the book on page 535. Change your 490 to that. All right, let's look at this one. So I have here both exponents are even. So we're going to do a power reduction, which is that sine squared is 1 minus cosine 2x over 2, and cosine squared is 1 plus cosine 2x over 2. If you ever forget which way the signs go, start with your double angle for cosine and just solve one of them. And you can see that here, my cosine is going to stay positive. So doing our substitution for sine to the fourth would take 1 minus cosine 2x over 2 squared. And doing my substitution for cosine to the fourth would take 1 plus cosine 2x over 2 squared. I'm going to square this, which makes that 1/4 and 1/4, which is going to give me 1/16 eventually. I'm going to square these two binomials, but I'm going to do something kind of interesting. Instead of squaring the binomials, which we could do, I could think about this as 1 minus cosine 2x times 1 minus cosine 2x, and this is 1 plus cosine 2x, and this is 1 plus cosine 2x. What do you see hiding here? What if I take that 1 minus cosine 2x and 1 plus cosine 2x? I get a difference of 2 squares. And what if I do it again? So now what I have is 1/16 comes out. This gives me 1 minus cosine squared of 2x squared. Now what do I know about 1 minus cosine squared of 2x? It's sine squared of 2x. And now I have 1 over 16th squaring sine squared makes it sine fourth. Here's my u. This case, my u has to be the 2x because there's no factor of cosine. I can't make my u sine. My u has to be 2x. My du is 2 dx. Need to multiply, divide by 2. And there is your nice answer. Again, if you looked at, say, v and made that sine of u, there's no way to get your dv because you cannot get the cosine u du. So we get a general reduction formula for sine to some power and cosine to some power. And these general formulas yield specific cases for the following. You do not need to memorize these. Do not do it, okay? By continuing our example on the previous page, which was this, and applying the rule for sine to the fourth, we get, remember, we had 132 on the outside, 1 over 32. And we get this, which gives us this. On page 536 is the integral of cosine to the fourth. So cosine fourth x dx integral, we can, first of all, do a power reduction substitution, and then squaring this binomial. If I think about this as 1/2 squared, that's 1/4. Now let's just square the binomial on the top. Gives me 1 plus 2 cosine 2x plus cosine squared of 2x. And when I take the 1/4 and distribute across, I get 1/4. Here I get cosine 2x over 2, and here I get cosine squared 2x over 4. And then I'm going to actually take each of these and get them ready for integration. All right, and there's going to be a aloha between here and here. Again, here is another double angle or power reduction. So doing our power reduction for this, let's remember that angle here is 2x. So cosine squared of 2x is 1 plus cosine 2 times the angle 2x, which is going to give us 4x. So now we have aloha going on here and here to get my integrals ready for anti-differentiation, and I leave that to you. At the bottom of this page are some very useful formulas. Okay, if n is odd, and we're looking at definite integrals from 0 to pi over 2 for cosine, becomes this. If n is even, it becomes this. And these formulas are also valid if you replace by sine. And you're asked to do that in one of the homework assignments. So looking at our reduction, sine cubed of x dx. Again, split off a factor. This is a Pythagorean identity, can substitute in. My u is going to be cosine of x. My du is therefore negative sine x dx. So I need to multiply, divide by a negative sign. At that same step, I'm going to substitute my u. Anti-differentiate gives us this, which gives us that, which is what we have above. Likewise, the tangent and secant functions also have reduction formulas. You won't use them often, but you should know and remember that when you're integrating, you've got some special integration rules for tangent and secant, so you need to pay attention to that. Okay, recall integral of tangent is natural log of secant, integral of secant is natural log of secant plus tan. You've got to remember that. So if I'm looking at the integral of tangent to the n power of x times secant to the n power of x dx, if n is even, split off a factor of secant squared. That's going to allow you to make a substitution that'll involve tangent. Your u will be tangent. Split off a factor of secant x tangent x if m is odd. That allows you to use the identity tangent squared is secant squared x minus 1 and make that substitution, letting your u be secant of x. And if m is even and n is odd, then you're going to reduce the integrand to powers of secant x alone. Let's look at this example here. Tangent squared x times secant fourth x dx. All right, n is even. I'm going to split off a factor of secant squared of x. This allows me to take this one and do a Pythagorean substitution. Now my u is going to be tangent x. My du is secant squared x dx, which I have, so there's my du. This is u squared times 1 plus u squared, or u squared plus 1. Distribute u squared, anti-differentiate, and go back to substitute in for u. Let's look at number 7. I have here m is odd. So I'm going to split off a factor of secant x tangent x. Now we know that to be the derivative of secant. It's going to make our u secant. So everything else should be in terms of secant. So I have secant squared here, and tangent squared is secant squared minus 1. So here's my u. This is u squared. This is u squared minus 1. Distribute the u squared, and we can again anti-differentiate. Simple. And our last one, where m is even and n is odd, we're going to get it in terms of secant alone. I can use a Pythagorean identity for tangent squared. I have secant alone. Distribute secant. Well, what do I do with this one? Well, this one is one of our formulas that's on the previous page, right there. So this is a case for remembering that there is one. What about that one? That is my integration for secant, which is this. So secant cubed is going to give me that part, and then secant of x is going to give me that part. And what can I do here? Well, I have 1/2 natural log of secant x minus tangent x minus 1 natural log of secant x minus tangent x. Guess what? 1/2 minus 1 is negative 1/2. Oh, little algebra there. For most of these examples, we've used u substitution in the evaluation of the integrals, but the examples in the book use an expansion method. So be sure to look at the book examples. And again, go back to page 536 for the Wallis formulas. You've got to do those. Your TPs for section 8.3, 1 through 4 all, 5, 7, and 19. See you next time.